In today's video, we're going to look at section 2.5, which gives us another way of calculating inverses of matrices, this time using the Gauss-Jordan method. The reason why this works is all down to looking at properties of inverse matrices. So we know that for a particular inverse matrix of any matrix A, I know that both of these properties are true. I know that whether I multiply A by A inverse on either the left or the right, I should get that identity matrix back, that n by n identity matrix that has ones on the diagonal and zeros on the off diagonal. In particular, I'm going to look at this first matrix equation. Okay. This is going to look somewhat similar to when we solved equations and put it in matrix form, where we said that when you had this system of equations, I could have my left-hand side matrix A, X was a column of my variables that I was trying to solve for, and then B was the right-hand sides of my equations written as a column. Okay. Each one of these was a matrix, it just so happened that X and B were column matrices. What I am doing in this first matrix equation here, I am trying to find A inverse. I know what A is and I know what my identity matrix is, but the question is, especially for these larger matrices, how do I find out what A inverse is? Well, I can write this exactly as I did here with my system of equations. But this time I have got these actual matrices instead of just column matrices. I've got square matrices, A inverse and my identity matrix instead of X and B. I am trying to solve for A inverse just like I was trying to solve for X. I'm trying to find out what A inverse is. And I know that my right-hand side is just the identity matrix. So I can solve this in a very similar way as I did before using Gauss-Jordan. When we used Gauss-Jordan to solve this system of equations written in matrix form as A times X is equal to B, I wrote A as my matrix on my left-hand side, I put a line, and then I put B on the right-hand side. I performed Gauss-Jordan until I ended up with ones on the diagonal on the left, and then whatever was on the right-hand side was my solutions to my equations. Similar thing here. I'm going to put A on my left-hand side, and I'm actually going to put a whole other square matrix on the right-hand side, being the identity matrix. I'm going to do exactly the same thing as before, where again, I'm going to try and get the identity matrix on the left, just as I did here. I ended up with the identity matrix on the left, and I ended up with my solution matrix, which was just that column matrix X on the right, in this particular format where I've got A times A inverse equals the identity. This time I want the identity matrix on the left, and then my solution again is going to be on the right, which in this case is going to be A inverse. So whenever you do this, when we did it first with that system of equations, I put A on the left and B on the right. I then tried to solve it and simplify it all the way down to where I had the identity on the left and I had whatever my solution was on the right-hand side. And I could just read it off as X is equal to this, Y is equal to this, Z is equal to this. Okay. In this case, I've got A on my left-hand side, the identity on the right-hand side, because my right-hand side matrix in this case is the identity matrix. I'm again going to simplify it so that I've got the identity matrix on the left, and this time my solution that is on the right is actually going to be A inverse, exactly like we had before where we instead ended up with X on that right-hand side. So it follows along exactly like we did before, it's just this time our solution and our right-hand side are actually both square matrices instead of just column matrices, but the actual theory works out exactly like we did before. I'm going to do a few examples of things that you need to watch out for, etc., and how we actually do this, just to make sure that everyone is comfortable with different things that you may come across in these problems. So the first example I want to do is actually of a 2 by 2 matrix. It's just a simple matrix, but instead of doing 1 divided by the determinant and then switching things around with A, B, C, and D, like we did in 2.4, I'm actually going to solve it using Gauss-Jordan and then also do it by using our method from 2.4 as well to show that it doesn't matter which way you do it for a 2 by 2, it works both ways. So I'm going to start out with the matrix A, which is 1, 4, 2, 9. Okay. Now, using our theory, I'm going to put A on the left-hand side and the identity matrix of the same size, it's going to be that n by n identity matrix, on the right-hand side. I am now going to use Gauss-Jordan to simplify my left-hand side to where I get the identity on the left, and then what I read off on the right-hand side should be my solution to that matrix equation being A inverse. It should give me the inverse of my matrix. So, doing Gauss-Jordan, we already have a 1 in the top left-hand corner, so we're fine there. I now need to eliminate or make 0 everything below that value. So I'm going to take row 2 as it is minus 2 times row 1. That should make this value here as 0. So I'm going to leave my first row the exact same, and remember you have to do this to both sides. You're going all the way along exactly as you did when we solved A times X is equal to B. So I am doing row 2 minus 2 times row 1. So 2 minus 2 times 1 gives me 0. 9 minus 2 times 4 gives me 1. 0 minus 2 times 1 gives me negative 2. And 1 minus 2 times 0 gives me 1. Okay. Now, I already have a 1 again in my pivot position on that diagonal. So I'm fine there. I don't actually have to do anything to that row. I don't even have to divide it through by a scalar because it's already a 1. So I've already done my forward elimination where I've got 1s on the diagonal and 0s below it. I now need to worry about the entries above the diagonal. So first thing that I need to do is to get rid of this value 4 here. I need to eliminate that and make it a 0. So I'm going to do row 1 minus 4 times row 2. So my row 2 this time is going to stay exactly the same. And my row 1 is going to become what my original row 1 was, minus 4 times row 2. So 1 minus 4 times 0 is still 1. And then 4 minus 4 times 1 gives me 0. Then I've got 1 minus 4 times negative 2. So that's going to be 1 plus 8, which will give me 9. And then 0 minus 4 times 1 gives me negative 4. I am now to the point where I have the identity matrix, the 2 by 2 identity on the left, and what I have on the right at that point should be A inverse. This is my solution. So that tells me that A inverse is equal to 9, negative 4, negative 2, and 1. At this point, you can go ahead and check, but you should find that A times A inverse should give you that 2 by 2 identity, and similarly, A inverse times A should give you that 2 by 2 identity. It doesn't matter which way around we multiply with a matrix and its inverse, you should still get that identity matrix back. You could also go ahead and do this on a calculator. So, to check this, you can say, okay, put in your matrix A, and then you can do A inverse exactly like we did in the video before. That will give you the inverse matrix back. Or if you wanted to do it this way, but check your solution at the end to make sure that you've done your whole Gauss-Jordan method correctly, what you can go and do is actually put this matrix So our original matrix A with the identity on the right-hand side, put that into your calculator and then run it through that reduced row echelon form. So where we did RREF of that matrix, it should then give you this matrix at the bottom. This is as reduced as it's going to get. So it should go ahead and do that for you, because everything below those ones is 0 and everything above it is also 0. It just so happens that you've got those extra terms on the right hand side where we don't have any pivots. So you could go ahead and do it that way just by putting this larger matrix into the calculator and doing reduced row echelon form of it. That's another way of checking. Or because we have a 2 by 2 here, we could go ahead and actually check using our definition of the inverse of a 2 by 2, and we did that in 2.4. So if A is equal to this matrix here, we said that A inverse is just 1 divided by, we do A times D minus B times C. So that will be 9 minus 8. And then we switch A and D and we make negative B and C. 9 minus 8 is just 1, so 1 divided by 1 gives me 1. And then that just leaves me with that matrix, which is exactly what we found by doing this Gauss-Jordan on those matrices put together with A and the identity. So go ahead, you can do it for any other 2 by 2 example just to prove that this works. So I would encourage you to do that. I'm going to do this for a larger system. So this time I'm going to use a 3 by 3 matrix. So let's say I have A is equal to 1, 2, negative 2, 1, 1, 1, 0, 0, 1. Okay. And I've got to find A inverse. So I take my matrix A and I put that on the left-hand side, and on my right-hand side, I put the 3 by 3 identity. Make sure that you take the identity matrix that has the same dimensions as your matrix A. And again, you're going to perform Gauss-Jordan. Okay. I already have a 1 in my pivot position. So then I have to make 0 everything that's below it. I already have a 0 on that bottom row underneath it, but I need to make this one a 0. So to do that, I'm going to do row 2 minus row 1. So at this point, row 1 remains the same and row 3 is going to remain the same because we've already got a 0 where we need it on that 3, 1 position. So I'm going to go ahead and keep row 1 the same. And then row 2, my new row 2 is going to be my original row 2 minus row 1. And remember to do this to both sides. So I'm going to end up with 1 minus 1 is 0. 1 minus 2 gives me negative 1. 1 minus negative 2 gives me 3. 0 minus 1 gives me negative 1. 1 minus 0 is 1. And 0 minus 0 is still 0. And I'm not changing my third row at this point. I am keeping it the same. Okay. Now what I need to do in this position here, I need a 1. At the moment I've got a negative 1. So I need to either multiply or divide through by a scalar in order to make that a 1. So what I'm going to do is I'm going to multiply the entire row through by negative 1, and that will give me a 1 in that position. So my row 1 is going to remain the same. That's not changing. Now, my row 2, I need to multiply the whole thing through by negative 1. So I'm now going to end up with negative of what my row 2 is here. So I'm going to end up with 0, 1, negative 3. And then my right-hand side is going to be 1, negative 1, 0. And I'm not changing my row 3 at this point, so that is going to remain the same. Okay. Now we've changed this pivot position to make sure it's a 1, and then what you would do next is make sure that everything below that pivot position is a 0. Well, that's already the case. We've already got a 0 below it. Okay, so then you would move on to your next pivot position, which is here. That's also already a 1. So we don't need to do anything else at this point. We have already done our full forward elimination. So now we need to look at backward elimination, meaning that we have to eliminate things above our pivot positions, starting with the last pivot. So I start again with this 1 here, and I'm going to make 0 everything above it. So row 1 is now going to become my original row 1 plus 2 times row 3. So I'm going to use this pivot to make this value as 0, but I have to, whatever I do to one particular entry, I have to do it to the whole row. So I'm going to do row 1 plus 2 times row 3. And again, I'm going to use this 1, that pivot entry, to make this negative 3 into a 0. So my new row 2 is going to be my original row 2 plus 3 times row 3. So I use that pivot position to eliminate that negative 3 to make it a 0. So my new row 1 is going to be row 1 plus 2 times row 3. So I'm going to end up with 1 plus 2 times 0 is still 1. 2 plus 2 times 0 is still 2. Negative 2 plus 2 times 1 gives me 0. Then 1 plus 2 times 0, still 1. 0 plus 2 times 0 is still 0. And 0 plus 2 times 1 gives me 2. And then my new row 2 is row 2 plus 3 times row 3. So I'm going to get 0, then 1, then negative 3 plus 3 times 1 gives me 0. 1 plus 3 times 0 gives me 1. Negative 1 plus 3 times 0 gives me negative 1. And 0 plus 3 times 1, it gives me 3. And my row 3 remains the same. Okay. And finally, I need to make this entry a 0. So I need to use my pivot in row 2 to eliminate everything above it. So I'm going to eliminate that 2. So I'm going to make my new row 1, my original row 1, minus 2 times row 2. So I've used that pivot to eliminate everything above it, but I have to do it to the whole row. So my new row 1 is going to be 1, and then 2 minus 2 times 1 gives me 0. 0 minus 2 times 0 gives me 0. 1 minus 2 times 1 gives me negative 1. 0 minus 2 times negative 2 gives me 2. And 2 minus 2 times 3 is going to give me negative 4. Okay. And then my row 2 and row 3 remain the same. Okay. So at this point, we now have my identity on the left-hand side, and what is on the right-hand side, therefore, should be A inverse. So that tells me that for my original matrix A inverse is now this matrix here. So negative 1, 2, and negative 4. Then 1, negative 1, 3. And 0, 0, 1. So this is the inverse of my original matrix A. Again, you can go ahead and multiply A by A inverse and you should get the identity. And similarly, if you do A inverse times A, you should get the identity. You can also plug it into a calculator to show that this is the inverse of the matrix. So you can type in A and then go ahead and find the inverse of that matrix. Or again, you can go ahead and take your original matrix that we had with the identity on the right hand side, go ahead and do the reduced row echelon form of that large matrix. It is a pretty big matrix, it's a 3 by 6. So you're going to go ahead and type that into your calculator and find the reduced row echelon form of it, and you should find that whatever is on your left hand side should be that 3 by 3 identity, and what is on the right should be A inverse. And that is what you should find for your inverse matrix.
The last problem I want to look at is a matrix that does not have an inverse. So what should we look out for when this actually happens with a particular matrix? So I'm going to take the matrix A this time, and it's a 3 by 3. Okay. I will tell you now that this matrix actually doesn't have an inverse. So when we go through the normal calculation of finding the inverse using Gauss-Jordan, I put the matrix A on the left-hand side, and I put the, in this case, 3 by 3 identity on the right-hand side. Your first step here, because we don't have a 1 in our first pivot position, there's a couple things you can do. I can either divide that entire row through by -2, and that would therefore give me a 1 in that position, and I could carry on as normal, getting zeros below that value of 1. Or in this case, I actually have a 1 below it. So what I'm going to do is I'm going to switch those two rows. So my first row is now going to become what was my second row, and my second row will now become my first row. I can then carry on with Gauss-Jordan as normal. So I'm going to make this a 0 and this a 0. I then look at what my pivot position here ends up being. I make sure it's a 1, and you carry on. You actually get to a point where, after a couple iterations of the Gauss-Jordan method, you'll get to this point. And at this point I have a pivot in this position, it's a 1, I now make the value below it a 0, so I'm going to add row 2 to row 3, and that's going to give me a 0 in that position. And I get to this point. I now have zeros on the left-hand side, but non-zeros on the right-hand side. If you remember back to when we were solving systems of the form a times x is equal to b, whenever I ended up with zeros on the left-hand side, but something non-zero on the right-hand side, we'll call it a for some non-zero a, then that told me that I had no solution here because my system was inconsistent, because it basically said that 0 multiplied by x equaled something non-zero. That's exactly what we get here. I've got a row of zeros multiplied by each column in my matrix A inverse would give me a non-zero right-hand side. Okay, so again, I end up with this weird thing that is inconsistent. So therefore, that tells me because of this inconsistency, A has no inverse. It is not an invertible matrix, therefore I cannot find A inverse. I want to go back to looking at these as systems of equations. So if I were to have this particular system, I've got this system. My coefficient matrix is actually the matrix that we just looked at. And then I would have x, y, z is equal to 1, 7, 4. Okay. This is my matrix A. It is my coefficient matrix. Now we've just discovered that A has no inverse. So that tells me because A has no inverse, I cannot figure out x by doing A inverse times B, because this actually does not exist. A inverse does not exist. So that tells me that x does not have a unique solution. Now, dependent on the right-hand side tells me whether I have no solutions or infinitely many solutions. When you went ahead and did Gauss-Jordan on this system, A times X is equal to B. Depending on what this right-hand side B is will determine whether I have infinitely many or no solutions. But I know I do not have a unique solution because A is not invertible. Okay. So again, you can do different examples of this. You can go ahead and try to find A inverse. If you were to do this particular one on a calculator, it would come back with an error whenever you try to find the inverse because it does not exist. I encourage you to go ahead and do some of these examples, particularly in the homework, and you will see how these different problems arise, especially when you go and try and find a matrix A that doesn't have an inverse. You'll come across exactly like we just did here, with zeros on the left-hand side and non-zeros on the right-hand side when you went to go and find A inverse using this Gauss-Jordan method. There will also be some problems where you'll try and solve systems of equations using this inverse if it exists. If it doesn't exist, then of course we can look at whether there are no solutions or infinitely many solutions. So I encourage you to go ahead and do a few examples of these, and of course go ahead and check on your calculator either by typing in the matrix A, finding the inverse that way, or by using the reduced row echelon form of these larger matrices where we have A on the left hand side and the identity on the right hand side, and finding the reduced row echelon form of that. If you have any questions, please let me know and I will see you in the next video.